Alright, what's happening, guys? So, been doing a lot of work with the wavefront simulator and a whole bunch of other things, but this one right here is going to be mostly about sixth orders, and just for you guys to get familiar with how a sixth order loads in the low frequencies, and on the higher frequencies how these chambers work together to get that wavefront out of the box itself. And to make the most important part here, guys, is you get to see that compression wave. You get to see the fact that all that air, the sound wave, however you want to visualize it, how it's actually loading up in the chamber. By that time the subwoofer comes back and compresses, and then it exits right back out. So you get to see in real time what that looks like. And then at the same time I'll be able to kind of move through frequencies, and you can see how different frequencies won't load. You won't get as much compression, and that's typical out of a sixth order. Even the most I mean, you could tune a sixth order to be more to have peaks, a solid peak, or you can have it to where it has that two peaks, one in the low, one in the high. So you can adjust your sixth order how you want, and depending on your subs and everything. But typically I mean, a sixth order is used for bandwidth, but they're also good for SPL. And like I said, for either the upper frequency or the lower frequencies. Most guys nowadays are going lower. And sixth orders can also be used for efficiency. So if your subwoofers aren't, too powerful, you would use a sixth order in place to get as much efficiency and as much SPL, as much bandwidth as possible. I don't know everything about it, so you could talk to other guys, see what they say about, people that actually ran in competition or have done lots and lots of these, and I'm pretty sure they would know much more than I would. I'm still learning. I haven't even built a full-on sixth order or anything like that, but that's why I'm here, to get really good with the programs and then cross-reference real world to my programs. I'll have a few more videos about that as well, but this one in particular, we're just going to visualize and get familiar with this wavefront simulator. So you guys can't see that now. So if you guys want to get good with the program, and if you want to kind of mess around with this simulator, download hornresp. It's free. Hopefully your computer can run it. Hopefully you can get it on there. And so we'll see what that looks like here. So you open up this window, go to tools, and you'll see it down here, wavefront simulator. There you go. Click on that and you'll get a screen that looks like this. So I'll quickly go over this, what it looks like. Let me move this in a better position. So it allows you to kind of just draw in a very pixelated format whatever shape of the walls that you have, and then you can add in a piston here, or a subwoofer, aka subwoofer, and you hit go and it'll show you what that pressure wave looks like. And keep in mind, guys, this is all two-dimensional. So a real system is three-dimensional. Pretty sure you guys know that, but it's important to realize that this is all just two dimensions, and you're missing an entire dimension when it comes to how these waves travel. But for the most part, if you do build your box to be mostly two-dimensional, I would say try your best to do it to where it's very two-dimensional, but keep in mind that that third dimension will have an effect. There will be some losses and some gains, and it's kind of hard to account for that when you can't visualize it. But let's keep focus here. I got a bunch of different saved alright, so we're back. So this one, like I said, it's very two-dimensional, but it will represent basically what a sixth order is doing, and it will represent the loading. So you're gonna see right here it says 1000 hertz. All this is relative, and it's to scale. So if you really wanted to try to get as best you can to scale, you could. But yeah, that's kind of a lot to talk about. But for the most part, like I said, it's a representation, and at this point, we can kind of pretty much take a 0 off here and assume that if I go to a frequency that's 100 hertz, we could say that's about 10 hertz, you know, so on and so on, to 20 hertz, 30 hertz, 40 hertz, so on. So to scale, right? So for this design, it's tuned to about 20 hertz. That's where its low side peaks, and then if we double that, it's being a 2 to 1. 40 hertz would be its upper range. So 10 hertz is a little bit too low, and we'll get to see what that looks like. And that's really what I want to show you guys as much as I possibly can with the very, very basic wavefront simulator. But I haven't been able to find anything that I can afford for sure. I'm pretty sure I can get some really hardcore wavefront simulators, but I can't even find them. And let alone, like, I'm pretty sure if I were to find them, I mean, they'd probably be in the 10K range. But I don't know. You guys let me know if you know any better. But like I said, all I know is this one's been free for the longest time, and I've been working with it as much as I can. And this is the culmination of all that. And now I get to kind of show it off a little bit and have some fun here. So let me know what you guys think. So we're gonna go ahead and run this program. And I'll show you little by little what these different bars do. So if you do try it out for yourself, you get familiar with it. So we're gonna go ahead and hit play, hit start here, and you'll see immediately that waveforms. You have your red and blue to show you your would be vacuum and compression or pressure. And right now we're doing a pretty much like a 10 hertz would be in a large enclosure, about 10 hertz. Most of you guys know, if you're tuned, to be 20, 30 hertz, 10 hertz is extremely low. Your subs are going to unload. You're not going to get very much power out of it. You might feel something, you might hear something, but it's out of the tuning range, so it's not going to go well. And that's what this looks like here. It's trying to get some of that wave out, but nothing's really happening. No compression, no loading, no pressure. So I'm gonna stop that here, and I want to show you guys another thing. Clear out the waves. So I can adjust the brightness of that. So if it starts to get, you start to get a lot of loading, a lot of compression in certain areas, that red and blue is gonna become darker and darker. The closer to green it is, that's more of a neutral. So let me show you that. We'll go all the way to the extreme brightness, 100%, so you can see it's really dark. So that pressure wave it's happening out there. It's getting out, but it's not as intense. And you'll see that when I dim it down a little bit. We'll go to 33%. So we see there's some pressure waves happening here, but nothing's really coming out. Nothing's really getting out of it. So this is good, because when we start to get that high compression, we can lower that brightness, and we can see exactly where that pressure is happening. And we'll see that more when I move on. Let me stop this here, bring that brightness back up. And then we have speed. So this is the speed of the simulation, or the amount of iterations per frame. So if I slow that down, let me clear the waves real quick, it's a little bit easier. So I'm going to slow that down to as low as it can go. You get to see that. Kind of like the Matrix, it slows everything down. We get to see the movements happening pixel per pixel with as much clarity as possible. Right, you get to see that bouncing right here. A wave just kind of bounced right back. Get your waves right here. You see this compression wanting to travel out. Going to meet up with this one here. It's a little too low, so it's lagging behind. A big pressure wave happening here, and it's trying to exit out. And you have a vacuum wave happening here. right? So let's speed this up because it's taking forever, right? We want to get through this. So now you get to see really quick movements there. You don't really get to capture any of that, but this will show you after a few cycles, a few waves, what's going on with the overall wave pattern. So let me stop this, clear the waves again. Let's zoom out a little bit so you can see what that means. So let's say I just want to see a few waves happen a little bit faster. So a few cycles have happened already. We got that first wave coming out, exiting. The second negative pressure, exiting. Alright, slow it down. There we go. Okay, so let's get into the good stuff now. Let's actually get into tuning. So this would be, like I said, a 20 hertz tune, low end, and we're gonna get to see that compression happen. I'm gonna go ahead and drop the brightness down to 20% because it happens really quickly. Clear the waves off real quick. All right. Turn the speed up a little bit. It's moving kind of slow. Turn that brightness down. So you can see we're starting to get some good compression, good vacuum here. Now here's the thing about a 6th order, guys. It will take a few cycles in order for it to start to begin loading. So take that information with what you will. There's a lot of SQ guys that, I mean, I don't know much about SQ, but I do know the fact that I believe they call it group delay. Anytime that it takes a delayed response from your point to your listening area, that's technically, I mean, that's technically distortion. That's technically, you know, you're not getting the signal immediately. So a 6th order kind of has this issue where it does take a few cycles for it to even build up full pressure. So like I said, take that information with whatever you want, however you want to perceive that. I'll go into some of the more SQ stuff later when I have a better way to explain it. But yeah, that's the one thing about horns and 6th orders and ported boxes, that it's a big no-go when it comes to sound quality, is that it takes time, and depending on your tune frequency, that should be relative to the time it takes to get from point A to point B. So keep that in mind as well. As you can see, a couple cycles have happened. We're starting to get a lot more loading. Air is trying to come in and out from both the front port and the rear port, and they're opposing each other perfectly, to where, just like if you were to shake like a spring, or maybe, you know, when you're pushing somebody on a swing, you start to get that resonance to happen. So this is what's happening right here. You see this corner is loading quite a bit. On the camera it looks pretty black, so I'm gonna dim this down some more. Like I told you guys, now that we're building up pressure, I gotta actually bring down the brightness so you can see that. So that's how you know that this is developing a significant amount of pressure. As you can see, a lot of A lot of loading right here in the chamber of the port. Not so much the actual chamber here, but the port itself. And even this corner is loading up, so you'll see as we raise the frequency up, this large chamber has its own node, which you'll have a high and a low pressure point. On the low tuning side you won't see that, but like I said, in the high tuning side you'll see that. Most of this loading and pressure is coming from this low chamber, you know, in combination with the subwoofer cone. So anytime you have a negative pressure coming out here, you'll have a negative pressure from the cone. The cone will be dipping in. Positive pressure, same thing. So we turn this up on the brightness. You see that right in the middle right here. You got lots of positive pressure, so the cone is coming in. Lots of negative pressure. And the important part is everything's wanting to exit out the front port. That's where you get all your sound, all your energy going out. So I think you guys get the point on this one. Let's stop that. Let's go up to the high tuning frequency and clear the waves. So it should be about 40 hertz, right? We'll keep the speed there. So this is double the frequency of your low side. So that means your low side should have basically two waveforms within it. And then it should be matching up to that higher frequency chamber. So you'll see this higher chamber. It should have two nodes here. We lower the brightness a little. So you can see now you have two different pressure points within this low side, which is good. That's what you want. You want your port pressure and your cone pressure to be equal when they exit out here. Otherwise you'll end up with a bunch of cancellation. But that's a little bit beyond the scope of this situation right here. That I don't want to go too far in explaining this and that and contradicting myself with a bunch of different things, but that's what this is here, so you can see, try to visualize what's going on. Now you can see right here, these are the nodes that I'm talking about. So within this higher compression chamber, within this higher volume chamber, you'll have that node where it's literally like vibrating within this chamber. What's important is that it's all exiting out. And that means that your front port is tuned properly with the rest of the whole system. This is all a circuit. This is all like if you ever design crossovers or anything like that, electrical circuits, they're pretty much exactly the same. They follow the same principles as an acoustic circuit. So I don't want to go too far with that, but you could think of like the port is kind of like an inductor, your chamber is like a capacitor, and just like a crossover has its filter point, this is exactly what's happening here. All this is a circuit. And the deal with the circuit is that if it's not, I mean, depending on what you're trying to do, if it's sometimes this waveform, it'll help by returning some of that energy right back to the cone. So when you see the high box rises, those numbers where you got those high box rise numbers, that's what's happening within that chamber, within that circuit. A lot of that energy is staying in the enclosure, and it's rebounding. It's basically it's vibrating like a spring, and it's returning that energy right back to the cone. Now, that could be a good thing for efficiency, or it could be a bad thing, because if your subwoofer, you're intended to have like a subwoofer that has 2,000 watts of capability, but your box rise is over 5 times, you might not get the full loading potential of that subwoofer. And that's typically what happens in like the transmission lines. You get a lot. You have a pretty much a straight pipe. There's going to be a lot of reverberation within that pipe. You're going to get a lot of return. It's acting a lot like a spring, so it's going to be bouncing back and forth. Like I said, that could be a good thing if you have a low-powered sub. If you're trying to be as efficient as possible, you want a lot of your sound to come from your cone area itself. That might be a good thing. There's always trade-offs, guys. It's a triangle. No matter what size cone, no matter how much power, it's always going to fall within this kind of a triangle. A lot like Ohm's law. Alright, so hopefully you got an idea there of those visuals. Let me clear out the waves again. Let me drop it down to an in-between frequency, so 30 hertz. Let's see what that looks like. I'll bring up the brightness a little bit, because you're not going to get as much loading in the center of this one. This one's designed kind of peaky, so you have that 20 hertz peak, 40 hertz peak. 30 hertz will be somewhere in the middle. It won't be quite as loud. There won't be as much loading. You'll get some box rise. And that's kind of what's happening right here. Is you have a little bit coming back to the port here. Some of that energy is rebounding. Some of it's getting canceled up in the higher chamber. And that's a big one, guys. That a lot of power is lost when you have too many nodes in a chamber. That's just basically cancellation. So anytime that energy isn't going somewhere, well, you're not transmitting the power. Which, once again, depending on what you're doing, depending on how you focus things, that might be a good thing. If you're not worried about SPL, where you have a tiny little single millimeter of a hole as your focal point, SPL really isn't telling you everything. You're just showing that you're able to concentrate all that energy to one specific point. You could have a really loud system that, let's say, like 418s or 618s that does 150 dB, and for whatever reasons, to some people it sounds louder than somebody that has a single 8 that does the same thing, 150 dB, somehow, some way. It's because of the concentration of energy. It's still able to put out that 150 dBs worth of energy. It's just doing it in a way that focuses the energy to that point. So think of like lenses in light. When you take the sun and you get a magnifying glass, you're concentrating that energy to one point, and it's the same amount of sun energy. It's just concentrated to one point. So it's the same principle, guys. So you can see quite a few cycles have happened. Now we're starting to increase in our pressure. It's starting to become much more heavy loading, to where I got to dim the brightness down a little bit so you can see it. And there's that node within this chamber here. And there's your 2 different frequencies within this chamber and port right here. So even at the 30 hertz where it's not quite tuned, over time it'll actually develop a little bit more loading, but it takes a little bit longer. crazy stuff happens here, guys. And once again, like I said, this is just a two-dimensional representation of that. Most boxes are a little bit more three-dimensional, where there's different cavities in different areas, different nodes happen in those cavities. Your car isn't a perfect square, it's got a bunch of strange shapes. So a lot of things are going on in your cabins, guys. You have a lot of deadening if you have your interior and stuff still. That's why you see these SPL vehicles, they're completely smoothed out, they're flat, they're rounded out in certain areas. It's all designed to focus and put a pressure point where it needs to be. All right. Right, so that's that. So now we got a little bit more familiar with the program and what it does and what a sixth order kind of looks like. Typical sixth order design. Now I have another design here. I'm gonna show you guys right now. I'm just gonna keep on trucking with this video. Appreciate you guys if you're hanging out and actually watching and listening. Whoops. Let's see, what do I got? Compare. Alright. So I didn't want to show this one, but I'm going to do it anyway. We'll see what happens. This is where the contradictions come in, and with the lack of experience and all that. But feel free to, if you feel like this is all bullshit or whatever, like, call me out on it, put some in the comments. I don't care. This is a learning thing for me, and I'm just expressing or showing what I'm seeing and what I'm getting at, what all this stuff is, what it means to me. And for those of you with more experience, what you've seen and what you've experienced, hopefully this is all a learning curve for everybody, and we can all kind of grow as a community through all this information, right? This is science in the making, right? So what I did here, from what I understand about systems, is that certain shapes and certain designs obviously have a different effect. And I see a lot of people just build and they kind of figure out what happens later, or they want to make changes and they don't understand which direction to go or what to change. Most people are following the typical just go bigger, go better, right? More amps, more power, more subwoofer, more cone area, bigger magnets, whatever. So that might not be the right direction to go. And like I said, depending on what you're trying to do, some people are just aiming for SPL, some people are chasing numbers, some people want sound quality, some people want more wind, and we got to clarify those things and really figure out, well, what the hell does that mean, right? And what I've learned is you have these different box designs, right? You have sealed, you have a ported, you have a transmission line, and you have a horn. They're all different circuits. They all do different things when it comes to the cone area involved and the amount of power applied, the suspension on that subwoofer, and then your overall dimensions of your enclosure and your listening point. So what this is supposed to represent here is 3 different sixth orders in alignment, right? So you can compare them next to each other side by side based on the program. All the same cone area, and they're designed in what I would say would be a typical large build. So you have your Yukons, your big SUVs, and they just have 6 18s stacked. I didn't put the whole extra subwoofers here and there, and I just wanted to kind of keep it simple. So this is what this is kind of designed to mimic, is that really long chamber and that higher chamber volume, higher tune volume, exiting out into the cabin, right? So let me go out, pan out so you can see. All these volumes are the same on the exit. They're different here on the loading chambers. And let me show you how they're different. So this one mimics a typical sixth order that you would see most people build. Probably the easiest to build. Very large chamber on the low end. Tuned port, to whatever low frequency, your upper large area chamber, flat. That's the big one. This is a flat design. So to me, this would be more like a transmission line because of the flatness. Because you have this large chamber that the wave can, the speed of sound is really fast, 768 miles per hour, something like that, right? You guys could do your homework, figure that out. But even though your 20 hertz frequency wave, your quarter wavelength, it takes some time to get out of there. There's a sound wave that's happening within this chamber, and you'll see the sound wave wanting to bounce around here. It's going to bounce around there. That's all lost energy. That's all power. That's all energy. Some of it goes right back into the cone. Some of it just cancels itself out. All kinds of stuff happens here, and that's what I want to show. If you design your chambers a little bit differently, you'll get different optimization. Like I said, sometimes you want that efficiency. Sometimes you want that rebound. Sometimes you want that high box rise. We'll call that efficiency or whatever. Sometimes you need heavy loading, and that's where these other chambers come in. Sometimes you need that pressure to escape immediately. Sometimes you need it to return and come back, so you get better loading at better frequencies. This is how you get bandwidth. And in this case up here, we have it looks more like a horn design, right? It's real thin from the get-go, and then it gradually, exponentially increases in the mouth region. And you'll kind of see how these all act differently when I hit the play button, and you get to start to see that wave happen. And these are roughly tuned the same, so 20 hertz low side, 40 hertz high side, but they all respond differently. And here's what I want to really show, guys, is that I haven't been able to prove it yet, but I do believe something. I believe that when you have a chamber this big, that length, you'll end up with the compression wave, right? That'll kind of get stuck in these chambers, in these points. And what I want to, the whole point to that is that if you have compression in a small region like that, you're going to have offset loading. So that means this subwoofer is going to see a lot more pressure than this subwoofer, and so on and so forth. So the further back you go, there's going to be a whole bunch of loading on one sub and nothing on another. And that's what I want to show you. I want to show you guys that be careful how you make your designs, and be careful when you, like, if you start to see a certain sub in a certain area blow, you might be having some issues with that design, and you might need to figure out a way to balance some of that pressure within your subwoofers. So if you guys know anything else about systems and pressure and things like that, so like in a large warehouse where things are ventilated, I'm gonna go ahead and let this play, because it takes a while for it to develop pressure and all that, while I blabber blah 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 blah. All right, let it play. So like in a ventilation system, like in a big warehouse, if you ever look up and look at the ventilations, you'll see that they have a progressive different diameters as it goes from point all the way out to the exit. And that's because without that, you'll end up with a whole bunch of different velocities at the very end, and you'll have some areas that are receiving a bunch of airflow, whereas others will get nothing. So that's going to be a major off balance, and it takes quite a bit of some calculating, some pretty heavy math to get all those velocities correct, making sure that the diameters are decreasing properly. And subwoofers at this size, and these builds, you're starting to get into that level. I mean, it's still small scale, it still works the same, but large scale for sure. So for those of you guys that are getting windy, or are really trying to maximize your SPL, or you can't figure out why that one subwoofer keeps blowing out in the corner, keep that in mind, right? So I'll let this build up some pressure. We're at 30% brightness, so you can see some loading happening on this one right here. See, you see that compression? You see that compression there? There's some pressure developing here. Remember, guys, they're all running at the same time, but they're all giving different loading. A lot of pressure happening in this one right here. This one you're starting to see, it just disappeared. So that's cancellation. This one, which is the horn, you see how darker red this one is? That's sound pressure. That's a sound wave exiting the chamber. That's good. That's what you want for like SPL or actual sound. You want to actually experience that wave. This is good. And that's why you see a lot of concerts, large concerts, still have a bunch of those bunch of horn-loaded subwoofers up in front. A lot of that sound energy gets transmitted outwards. Not to say that horns are better. It takes a significant amount of space and design work to really get a horn to work properly. I'll let it run a little bit longer so you guys can see that. A lot of pressure building up in this chamber right here. You see how this kind of like, it looks like it just dropped. That's a wave that's happening right here at a much higher frequency than the tuning frequency. So that's basically that sound wave bouncing within. That would come out as a really high pitch harmonic. I'm not really sure if you would hear that, but for the people that talk about how horns kind of have that horny sound, that's usually what happens. Is you get a harmonic that bounces around. Even some ported boxes, if your boxes, some of you guys that had to add some dampening material in there to minimize those boxy tones, that's what that is. That's that sound wave pretty much just bouncing around within that cavity, and you can actually see that happening right here, which is what I find interesting about the program. Alright, let me zoom out a little bit. So we're still at tuning frequency. The speed's a little bit higher. And what I want you to see in this case, guys, is just the amount of output. So like I said, with this lower design, which is more like a T-line, you're more than likely going to have really high box rise, and you're going to get less output because of it. But this design would probably run more efficiently, so it would take less wattage. Or you could run weaker subs that don't require as much power, smaller magnets, lighter weight system, and you'd still get good output overall. Whereas this one up top is a little bit more in the middle. It's designed better for loading, so you could put a little bit higher output subs. And then just the opposite with the horn. It's going to be intended for heavy loading, heavy output, but it might require more power, more space. Alright. So let's go back and I'll do a higher frequency just so we can see what it looks like. Bring down the speed. Bring down the brightness a little bit since you're familiar with what it looks like now. See that wave bounce? So we're at a much higher frequency this time. Just pay attention to any kind of nodes that you can see here. So this would be your node. So your compression is happening right here. With this design, like I said, you'll see a lot more of that, a lot more energy happening within the chamber itself. Some of it's going to rebound quite a bit. So there's your box rise. But a lot of that power is staying in this area and not quite exiting. This one is a little bit more in the middle. We're getting some compression happening here, but we're also getting some of that power to actually exit outwards. And then with the horn, it's significantly, you know, you're getting pressure, you're getting loading, but it's coming out, it's exiting out. We drop down that brightness. 6%, it's really low, but you can still see that little that node that happened right there. That's what I want you guys to see. Depending on your design, your box may have an offset loading between subwoofers. You see how you're starting to get pressure here develop early? This subwoofer is going to see that first. Whereas in the horn, that pressure is kind of, it's divided up evenly, a little bit better than these designs right here. Going back to the ventilation systems, you want to make sure that everything's balanced out from the beginning to the end, so you get the correct velocities. Same thing with like car engines. When you design an intake and exhaust port, there's a whole lot of factors. That's what your dang, I forget what it's called now, dynamic chamber or something like that, but it almost looks like a ported box where you have a large chamber going into the runners. But all that stuff has to be tuned properly, guys, so each cylinder receives even pressure while there's airflow. So a little bit different from a subwoofer, because a subwoofer is just, you know, in and out and in, whereas you know, a car engine has velocity coming inwards. It has a lot of different flow patterns, and the fact that the air wants to turn corners, bend corners and stuff like that, that changes a little bit how the velocity moves. Where you might see some of that in some of these designs as well. And in your exhaust, a lot of things happen within your exhaust to make sure that you have proper back pressure, right? This is kind of the same thing right here with the horn. You're getting good back pressure where it wants to, you know, pull and push when it comes to loading. And over here on your T-line, more of a T-line design, that back pressure is actually going to be even higher, and it's going to want to pull and push on those subwoofers a little bit more. Like I said, that's your box rise. All that energy staying within, which, like I said, could be a good thing if you're going for efficiency. Could be a bad thing if you're not maxing out your total power. And you see that happening right here, right now, where there's a lot of pressure. Even we're at 6%. A lot of pressure is happening in this cavity alone. None of it's coming out. So you're getting a lot of work done here, and you might not even be, you probably wouldn't even see that in your wattage, like I said, because this is all box rise now. This is all just playing and fighting within itself. Over here it's a little bit less, getting some loading, some of it's exiting out. Same thing with the horn. Turn that up, you see it a little bit better. Turn it down. 0%. It's a lot of pressures happening in this guy. Whole lot. So once again, this is a extremely low resolution wavefront simulator, extremely low resolution, but even in this, we can still get pretty close to seeing what that would look like. And I hope this helps you guys out, you know, gives you a little bit more of an intuitive approach when it comes to your designs, and what could be happening with your systems. If you do have a big 6th order build, or you plan to build a big 6th order, or any design for that matter. I do have a couple of ported wavefront simulations that I want to get into, but they're not as tricky as these guys, so I encourage you to do them yourself and try them out. But I'll do a few of them to see what they do, and just so you guys could take a look. But I think that's it for this one. I got a couple more videos on the way. I'm trying to cross-reference what has been done in real life. I plug in the numbers in horn response, see what the curves look like, and then compare that to real life numbers. I'm doing it with my own systems as well, and that's to really get good at the program first. So if I do have the numbers, the right TS parameters, I could dial it in and build an enclosure theoretically first, and then expect to have high quality representation in reality. So that's the whole point of a program, right guys? Like, what's the point of having a program design, get it all built and done, and it doesn't even come out like you expected it? So what I'm finding is that cabin gain is a big thing. It changes a lot of what you expect in the program, and it's on the plus side. So if my program says, yeah, tune to 30 hertz and 120 dB, I tend to see that with cabin gain, I'll see crazy high numbers, So like in my own setup, it's not showing that I can pull off a 140 with a single sub, but in reality I did. So got to make sure those numbers are dialed in, and yeah, because some of the builds that I've been doing on the program, I'm seeing that I can achieve 145 dB at 20 hertz and so on. And I'm kind of skeptical, right? Like, I don't believe that it's possible, but we're gonna get to the point to where I actually build some of these enclosures and see what we're gonna see what's gonna happen. So, but anyway, we'll do more on that. I got another video coming out with that specific. So letting this run so you guys can see we're at 0% brightness. You can see nothing's really changed here. As I told you, a few cycles, a few waves, you'll start to get more and more compression. That compression increases. So just like you would push somebody on a swing, you wouldn't start out immediately at 100%, right? You add in more power, and eventually you'll max out. Same thing happens here in your 6th order, or even your ported boxes. A few cycles of that cone movement, you'll increase pressure. You'll get more air in, more air out. The offset increases. So this is what you're seeing right now. In this design, it's canceling itself out. It's all staying here. This design, you're getting some power exiting out. A really high compression in this area. Same thing with the horn, because a lot of that power is exiting out. There's not as much loading here because of the design. You're not getting that same loading. You're not getting that same rise. At least these are my assumptions. I mean, this is, like I said, a very low resolution program, but yeah, I just wanted to share this with you guys because I'm working pretty hard on getting these numbers dialed in, doing my math, doing my homework, converting things, sitting here and doing a bunch of different designs. This design took me hours. So hopefully somebody out there could get it done better, faster, and will be willing to share that. But yeah, appreciate you guys if you stayed for this whole video. Once again, long video, but I'm trying to get as much information out as soon as possible, as fast as possible. And yeah, here we go. Thanks a lot. Next one.